Solar magnetic energy. Magnetic fields within a sunspot can be as strong as B equals 0.4 Tesla. By comparison, the Earth's magnetic field is about 1 over 10,000 as strong. Sunspots can be as large as 25,000 kilometers in radius. The material in a sunspot has a density of about ρ equals 3 times 10 to minus 4 kilograms per meter cube. Assume mu for the sunspot material is mu0. If 100% of the magnetic field energy stored in a sunspot could be used to eject the sunspot's material away from the sun's surface, at what speed would that material be ejected? Compared to the sun's escape speed, which is about 6 times 10 to 5 meters per second, and hint, calculate the kinetic energy the magnetic field could supply to 1 meter cube of sunspot material. Okay, so how much energy is stored in the magnetic field of the sunspot? We know the magnetic field energy density. This we show with lowercase u sub b, and it's equal to magnetic field magnitude squared b squared divided by 2 mu 0 permeability of free space. Now, how much is the magnetic field energy stored in the hot spot? Let's think about that. The total magnetic field energy stored in the sunspot this I show with capital U sub b. That's the energy density, lowercase u sub b, times the volume of the sunspot, which can be written as b squared volume divided by 2 mu 0. Okay, so here V is the volume of the sunspot. The problem suggests we can take 1 meter cube, but as you will see, the volume will actually cancel in this calculation. What about the mass of the sunspot? The mass of the sunspot is m, which is its density ρ multiplied by the volume v. Density is mass divided by volume. Now we're assuming that all of that magnetic field energy, capital B squared V, volume V, divided by 2 mu 0, is converted to kinetic energy, which is 1 over 2 mass of the sunspot times its velocity squared. Now for the mass, I can substitute its density times the volume. So this is 1 over 2 rho v velocity squared. The volumes will cancel, as you can see here. So I'm going to obtain the speed. Also, these 2's will disappear. Speed is b squared over rho mu 0 square root, or b divided by square root of rho mu 0. We're assuming the sunspot permeability is mu 0. Okay, so if I plug in the numbers, let's see what this speed is. V is equal to The magnetic field on the surface of the sunspot is 0.4 Tesla. The density is 3 times 10 to minus 4 kilograms per meter cube. The permeability of free space is 4 pi 10 to minus 7 Henry per meter. So we take the square root of the denominator and we will obtain a speed v is equal to 2 times 10 to 4 meters per second, roughly. And how about the escape speed from the sun? The escape speed from the sun is 6 times 10 to 5 meters per second. As you can see, this is 30 times v. So compared to the escape speed, this is rather small. Okay, so in this problem, we're talking about magnetic fields within a sunspot. These can be as strong as 0.4 Tesla, about 10,000 times greater than the Earth's magnetic field. And sunspots are 25,000 kilometers in radius. They can be very large. The density of the material is given, and mu is mu0, and 100% of the magnetic field energy stored in the sunspot is to be converted to kinetic energy to eject the sunspot material away from the sun's surface. And the escape speed is given, so we're asked to compare it to the escape speed. So what is the ejection speed here? The stored energy density is b squared over 2 mu0. Normally this would be mu, but mu is equal to mu0. Magnetic field energy stored in the sunspot is this energy density times the volume of the sunspot. So b squared v over 2 mu0, which is to be converted 100% to kinetic energy, 1/2 mv squared, or 1/2 rho volume speed squared. So volumes cancel, 2's cancel, so we find the speed to be b over square root rho mu0. And substituting the values, we obtain 2 times 10 to 4 meters per second, which is 30 times less than the escape speed from the sun's surface.